This video looks at an alternative way of handling constraints when you're doing tracking problems. So what we've done in the previous two videos is we demonstrated how you could incorporate constraints into an OMPC or SOMPC algorithm. And in simple terms, what we said was an easy way is to form an autonomous model for the predictions and then express constraints at each sample using some inequalities. And then what we can do is we can use a standard admissible set algorithm in combination with these two in order to form a finite set of inequalities which operate over an infinite prediction horizon. However, what we found was that when we wanted to tackle tracking scenarios, then this approach seemed to be somewhat inflexible and not suitable for online implementation. In particular, it didn't handle changing targets and changing disturbances. So what we're going to do in this video is we're going to show you an alternative way for forming the MCAS, which more easily incorporates a time-varying target and a time-varying disturbance. Now, what we should say is, while this approach is simple and easy to code, it does also have its own weaknesses. The difficulty then with doing constraint handling with a dual mode approach is that the predictions evolve over an infinite horizon, and consequently we can only be sure that the optimal solution that we're coming up with is valid and feasible if it satisfies constraints over an infinite horizon. Now, the previous video used admissible sets to capture the required inequalities to guarantee this happens, but admissible sets are defined for a fixed scenario and thus do not allow time-varying components, such as the steady state changing. And the problem we've got is if you look at the sample constraints that you're dealing with, you'll notice every sample there's this term here, R minus D, which affects the steady state values of the input and the state. And any time that R changes, or any time that D changes, then the corresponding expected steady state changes, and therefore the required admissible set will also change. Now, in practice, we know that admissible set algorithms actually converge after a finite number of iterations, and that can be proved for cases as long as the steady state is strictly inside the boundaries. The number of iterations of the admissible set algorithm required is going to be linked to the closed loop poles, are they fast or are they slow, and the proximity of the steady state to the constraint. But the key thing is we know it requires a finite number of iterations. Now, if I take an arbitrary example, let's say the closed loop poles are of the order of 0.8 to 0.9 in magnitude, then what you will find is the iteration count is likely to be of the order of 10 to 20. And it's only going to go above that if you do something perverse, like put the steady state on a boundary or make the poles very, very slow. Now, what this means is if I simply define the sample constraints for the first, and I'm putting an arbitrary number here, 30 to 40 samples, then I know that must capture the MCAS, because I can get the MCAS normally with 10 to 20 into the future. Now, this is a bit ad hoc and a bit simple, but the thing is, as you see, I've written at the top, it's pragmatic and it's simple. How do we predict then? So first of all, let's write down our control or our prediction equation. So this is standard, I'm not going to dwell on it. And then what I'm going to do is I'm going to substitute in for the steady state values of the state and the input, which I can predict, and they depend upon the target and the expected value of the disturbance. And what I can do now is I can write the prediction equations in terms of the real state, not a deviation variable. And here's the key thing: the term R minus D and my perturbation term C. Now, if I do that, so I've just written down what my model is, you'll notice my model has essentially now got two inputs. It's got this R minus D and it's got this C. Now, I can therefore form predictions for how the system will behave, and those predictions are going to have three distinct terms. They'll have the dependence on the current state X, the dependence on these future terms C, and the dependence on what I think the value of r minus d is. Now I'm not going to go through prediction because that was done extensively earlier, but the key thing is I can write down these prediction equations very, very easily. So that's step number one. Next, what I'm going to do is have a look at my constraints. Now if you look back to the first few videos in this chapter, and I've mentioned here video 5.3, you'll notice we said input constraints, for example, can be written down for every single sample in some form like this. But it's convenient to write this in a more compact form, a bit like this. So we had a matrix Cu times the vector of future inputs u less than or equal to some vector du. What I did then is I said, well, I can write down an expression for my future inputs, and in this particular case the expression I've got is something like this. And so now I can simply plug this into here. So my inequalities on the inputs can be written down with an expression a bit like this, and the key thing is I can put whatever prediction horizon I like into this, and that will simply affect the definition of PU, HCU, QRU, and so on. I'm not going to reorganize this because that was done in earlier chapters in different scenarios and is straightforward. So what can I do? If I've got input constraints, something like this, state constraints, something like this, then it's easy to show that I can ensure those constraints are satisfied for the first n samples. So you'll see n samples here by inequalities of this form here. Now you might not like the particular terminology. The terminology I've used here is what's used in the code SOMPC_constraint. So you'll see there's some matrix times my degrees of freedom, see future. On the right hand side I've got something which is fixed, and that fixed bit will depend upon the actual limits u upper bar, u lower bar, x upper bar, and then I've got some term which multiplies on xk and r minus d. Now some of the other code, if I use a more conventional description, I could say that my SMCAS is given using this terminology here. So you'll see I've got n times c future plus mxk plus vr minus d less than or equal to d fixed. Now these two are equivalent, and you can use the formulation that suits you best. So let's do a comparison of this pragmatic approach versus the admissible set approach we did earlier. So the admissible set had the advantage it was unique, it was efficient, it was easy to remove redundant constraints. The key word here is offline. However, it was only defined for a fixed r minus d, and if r minus d changed, then you had to recompute the whole set, which is a pain and is non-trivial. If I use this pragmatic approach, first you need to make an arbitrary choice of horizon over which you're going to ensure your constraints are satisfied. You cannot easily identify and remove redundant constraints, and the reason for that is that r minus d is not determined, it's variable, and therefore it's not obvious what horizon you might need, nor which constraints might be redundant. However, it does not need to be updated as r minus d changes, because the dependence on r minus d is fixed, and that's the key advantage. This is the reason that you might want to use the pragmatic approach, and therefore the code is a bit more flexible. So here's my point. If efficiency is not important, that's online efficiency, and that might be the case where you're in your office and you're messing around and trying a bit of this and trying a bit of that, then the pragmatic approach can be quite useful. If efficiency is really important, you're going to want to be looking at admissible set approaches. Some numerical examples then. Now these are then, I've called it OMPC old subfolder, so I'll just go and show you these so you can see what's going on. Into the wrong window there. This is the window we want. So first of all, if you look at SOMPC_data, what you'll find is that there's a file which basically calculates the predictions for the state and the predictions for the input, and you'll see the form they take: a dependence on C, a dependence on Z, a dependence on R, and a dependence on D. So I find these prediction matrices, and then I simply plug these in to, I've called it here, SOMPC constraints, along with the limits, and I end up with these matrices CC, dfixed, and dxo, and the constraint inequalities are given like that. So it's a very simple approach. Now, the key thing you want to notice is that there's this argument npred, which basically says what horizon am I going to use to define these prediction matrices, and that's a choice that you need to make. It's not fixed. Now we've got 3 examples that you can test this code work. So video 511 example 1, if I run that, what you'll see is that set point is changing, and this is just to illustrate it deals with changing set points, and you'll see that C is non-zero, so it's actually doing something. You'll notice the inputs do indeed hit the limits where key things are happening. So where there's a set point change, the input hits a limit, and the constraint handling is operating. We get a non-zero disturbance signal happening around here. You can see the impact here, and you can see the input saturates. And we have a change in set point here, and again you see the algorithm is working. 511 example 2 is just a different example, but we can run that. And again, this is multivariable, 2 inputs and 2 outputs, and you can see that the set points are changing. That's these black lines, and you can see that the input or the constraint handling is active. You can see that from the limits here. You can see that from CK not being 0 down here. There's also a non-zero disturbance signal added in. So the algorithm works with time-varying references, time-varying disturbances. And finally there's an example 3 here, just for completeness, and again you see the same pattern. We've got changing targets, changing disturbance, and the algorithm is quite happy, nothing changes. If you go and look at the particular algorithm, you'll see the algorithm does not update the set at any point. It just uses the set we've got here, CC, we've got this dfixed, and we've got this dxo term times z times r. Okay, so let's go back here. So these files demonstrate that the set point and disturbance can be modified online without, and this is the key thing, without any change to the inequalities for the constraint handling. The downside is the rather large number of constraints, and many of these will be redundant, and therefore the potentially conservative choice of prediction horizon for the constraint handling. But it does avoid the need to predefine limits on the values for the target and the disturbance, and you do need to do that if you're using admissible sets. So it makes your life a bit easier because you don't have to define things that might be hard to define. So remark, it's not obvious which inequalities may be redundant because these inequalities put no limits on r minus d, so you can't so easily remove redundant constraints. Now, it would be easy, however, and this is a danger, to propose a value for r minus d such that the MCAS above is empty. And that's a danger, and you'll end up with infeasibility. That's a discussion, however, for a later chapter. So in summary, this video has given an alternative to admissible sets for constraint handling. The assumption is made that using the insight from admissible sets, that we only need a finite horizon to capture the infinite horizon, we know that constraints do not need to be tested explicitly beyond some horizon n. But unfortunately, this particular horizon n will vary with the scenario, with the choice of set point, the choice of disturbance, and so on. But what we can do is we can choose some arbitrary large n and say I'm fairly confident that if I ensure the predictions meet constraints over that horizon, then I've captured the MCAS and everything will be alright. And by doing that, I can give myself some simple code for implementing constraint handling. And the key thing here is the set does not need recomputing each time the set point and disturbance changes, because the set is defined in terms of the set point and disturbance. Now we should finish by saying the focus here is on giving you a pragmatic approach. We're not pretending it is in any way rigorous, because pragmatic approaches are often enough if you're just doing initial testing, thinking, playing around, and so on.